In this track, focus more on research topics. My name is Lukas Malina. I am from Brno University of Technology, and I'm here to talk about cybersecurity in post-quantum era. So let me firstly say a few words about our project, which is dedicated to this topic. Actually, this project is with Estonian partners, and also this is the cooperation of Brno University of Technology and Red Hat. And this project is more or less for like building the networks and good relationships in the research and innovation. And we have 6 research challenges, and one of them is, of course, post-quantum cryptography or quantum-safe cybersecurity. And this will be the topic for today's short talk, which will be approximately about 35 minutes. So, what about our motivation? As you know, today there is a lot of news about developing and innovation in the field of quantum computing and what means for the current cybersecurity and for the current protocols what we are using every day. It means a lot because in case that some really functional quantum computer will come, then we have the problem. Everybody have the problem because everyone use, let's say, secure connection in HTTPS, right? So everyone should be aware if some quantum computer will be in the world. But what is mean in technical? We will talk about that. So basically, quantum computers and current state. At now, there are like a lot of big companies which are trying to build the quantum computer. For instance, Google, for instance, D-Wave, or for instance, of course, IBM. But all of these quantum computers are still not ready to be efficient to crack all things in cryptography. And now we have the oldest, which is the D-Wave, but D-Wave is based on a different approach, which is more or less like analog computer, and even it works with thousands of qubits, it's not like able to compute short algorithm, which is like essential for cracking current asymmetric crypto. But another companies or like big teams, this is not only about the IBM and Google, these teams are conducted from universities and researchers, so they are working on actually really quantum computers, and now we have the functional quantum computers with hundreds of qubits. But still, this is the good news that these low amounts of qubits are not very like efficient to solve short algorithm and crack the asymmetric crypto. And about the short algorithm, it was defined in 1994 by Peter Shor, and this algorithm is basically jeopardize all asymmetric crypto. And why is that? Because this algorithm can crack basic math problems used in asymmetric crypto. It cracks factorization and a digital algorithm problem. So this means for us that everything which is used for authentication based on certificates and for key exchange will be now like not secure, and we need to find some substitution and secure options. But as I mentioned, we still don't have the quantum computers which are able to, let's say, fully use short algorithm, because there is the estimation that, for instance, if you would like to crack RSA, which 2000-bit keys, you need the really functional quantum computer, which 4,000 qubits, perfectly working, and then, okay, you are able to crack it in the seconds. But this is the still big problem. Now we have only 100 qubits, and there is the problem that quantum computer is still working with certain probability of mistakes. And this estimation for 4,000 qubits assume that the quantum computers will be without the mistakes, because you need to do the process without the mistakes, and then you are able to crack it in the couple of seconds. So this is good news for us, for the security experts, that we are still have the time to be prepared. And there is also another algorithm which is less known, and his name is Gruber algorithm. And this algorithm jeopardizes also symmetric crypto. Why is that? Because this algorithm is more general, and he downgrade the problems for, let's say, finding the secret keys by brute force to this assumption. And this algorithm can jeopardize symmetric crypto, but we have the simple solution. We just need to use the longer keys. So symmetric crypto and hash functions are still okay, because we can only just use and increase the sizes of the keys. So what about approaches and countermeasures against the quantum computing threats for the cybersecurity? We have basically two options or two fields which are be helpful in quantum era. We can use quantum cryptography, also known as quantum key distribution. This approach is very, very old, and it's only just to serve us to exchange the keys. If you know somebody, Bennett and Brassard exchange protocol, so that's it. You need expensive devices. These devices, these sets of Alice and Bobs, cost like 100,000 euros, so it's very pricey, and it just to serve for key exchange. But what about the signing? We need to signing, we have the software updates, so then we have to sign the packages. We need also authenticate. We need some certificates. So quantum cryptography based on QKD is not have the answers for this. But what field have the answers? Post-quantum cryptography. Post-quantum cryptography can be run directly on the current computers, current platforms, because this cryptography just to look on the mathematical problems and construct cryptographic schemes differently that can withstand Shor algorithm and quantum computer attacks. So quantum cryptography, post-quantum cryptography has the cure for all problems what we have, and therefore NIST institution 5 years ago start with the standardization and just announced the open calls to find the new standards which can be good substitutions in the future. So let's talk directly about the post-quantum cryptography. And as I mentioned, this crypto solves everything in cybersecurity and prepare us for the post-quantum era. It's fun fact that the post-quantum cryptography is here very long. It's 40 years old. Some schemes are very old, and but these times when the quantum computing have the booms in the news, so then a lot of researchers started to more pay attention to this. Post-quantum crypto can be divided to a couple of families, couple of approaches, and we will focus on these which are also present in the standards from the NIST. So one biggest family is lattice-based cryptography. This crypto uses the lattices. It's high-dimensional grids, and it used the special problems when just the small change of coordinates like cause some very hard problems to find the secret or just to forge the signature or crack the ciphertext in the schemes used these assumptions. This figure just illustrates three-dimensional lattice, but it's not very good to imagine how it looks like in the real, because the dimensions are, there are more dimensions, of course. This is only the illustrative picture with the very simple lattice. And as the lattice-based crypto is very popular, so there is a lot of schemes, a lot of proposals, and a lot of proposals just also come in the NIST post-quantum crypto calls. And here is some list. I don't want to be too much specific and boring you, but this is just for your imagination that a lot of schemes show up. Also, very remarkable family is code-based cryptography. This family is very long. It's as old as the usually common asymmetric cryptographic schemes like RSA, which you know, or DSA algorithm. And this family use codes which are more or less known in the link layers when you send a message and then you use the autocorrection codes and just to solve some mistakes. So this family is also used for the post-quantum era. And the last big family is the hash-based. Why is this family such popular and very important for us? Because the schemes are also like quite old, and it was proven by time that these schemes are like safe. So this is also something which we will use in the future days. And here is just the comparison of all families. On the top you can see the more mature families, which is the old ones and very used ones. Code base is in the middle, but it is only just before because some schemes show up later after Michaelis, and lattice-based, okay, N2 is also like almost 30 years old, right? But some newer schemes which are used in the standards are also quite young and needs to be like the more explore if doesn't have some mistakes and errors. And multivariate cryptography and isogeny-based cryptography is less mature, and also it was proven by many teams that these schemes sometimes contain bugs and mistakes and are not safe. Even some schemes here was considered like the standards, but some research teams recently in this year just proved that some schemes are not safe and that schemes had to be withdrawn from the competition. And that brings us to the NIST post-quantum standardization. In the first round, there was I don't know, maybe more than 40 submissions, but some submissions was like correct and don't promote to the second round. In the second round, there were 26 semifinalists, and last year, NIST announced 4 candidates for the standards. What it means? That means a lot. Now, the NIST just to point to some few schemes that, okay, these schemes will be probably next RSA, next DSA signatures. So now, from the last, last year, everybody in the field just to work with these schemes, just to implement these schemes in hardware, in software, just edit these schemes into the libraries. We will show some progress in the libraries later in this speech, but The red ones are the winners, are the candidates for the standardization. The interesting fact is that the NIST choose only one candidate for the key exchange, just the substitution for Diffie-Hellman exchange. And this is the Kyber scheme. And the digital signature, NIST choose 3 schemes: Dilithium, Falcon, and Sphinx Plus. You can also see that the lattice-based have the candidates for both purposes, and for the digital schemes, they also have the hash-based schemes, which is Sphinx Plus. These schemes has own pros and cons, and I assume that NIST will be standardized all, but will recommend for different use cases, different schemes. And because they point only just for one CAM scheme, which is the Kyber, they still open the door to these orange schemes, which is the classic McAleese, Bike, and HQC scheme as the alternatives. Why they do that? Because in case that the lattice-based family will be in the future some bug, some mistake, then we can simply start to use something from the different family, which is the code-based McAleese or Bike. We did, and a lot of researchers in the field did some estimation, some evaluation, because we are curious which schemes will be like good candidates and doesn't affect too much the performance and also the overhead. I mean overhead in the sizes, because the post-quantum crypto is not just about performance increase and that all algorithms are quite massive considering the number of cycles, but these schemes usually have the much bigger sizes of keys and of course then sizes of the signatures. So as we use only like tens of bytes for RSA signatures or ECDSA, now we will use to, or we need to use to on the thousands of bytes of the signatures. So these signatures will be more massive, and it could be the problem for the fields like IoT or some constrained devices or constrained protocols such as Sigfox, LoRa, where you have only just few bytes for the message which are like communicated between the nodes. And this is just the numbers. You can check the presentation. I put it to the chat, so we don't need to like spend too much time here. And just now, let's proceed with how the institutions across the world looks on the post-quantum and what should be done. As I mentioned NIST. NIST started everything. Then American NSA, National Security Agency, just released the new proposal of the Commercial National Security Algorithm Suite, version 2.0, which says that we should directly just start to use post-quantum cryptographic schemes and exchange these schemes in all protocols and stop use the old common schemes like RSA and ESDSA and so on. But European institutions like French NC, German BSI, perhaps also the British, have the different view, a little different view. They are more cautious, they are more like conservative, and they say, okay, let's start to exchange these schemes, but let's do that in the hybrid approach. Let's implement these schemes in parallel and do the hybrid signatures, do the hybrid key exchange, because they are still not like convinced that the post-quantum crypto could be like the safe in the next 20 years, right? So they are like more a little conservative in this. But all these institutions all just announced that the time for the transition, time for the migration should be soon. Should be since 2025 and should end in 2030. So this is pretty in after next year, right? So we should be like prepared, and we should like only just also take account this in our projects. And also check NewKeep also somehow works with these recommendations and will soon announce own view and how should be done in the Czech Republic. And after 2030, I think that we will be use only just the post-quantum crypto. If not, perhaps it will be proven that quantum computer is not like feasible to build, then we are okay. We don't need to do that because the post-quantum crypto adds the bigger sizes and adds the cycles, but it seems that we will migrate to this. And in this table, you can just compare simply what should be substitute. So for key establishment, when the sessions just built, so old RSA or EC Diffie-Hellman or Diffie-Hellman just will be substituted by Kyber. And this is just what says Americans, what says NSA, right? This is not like definite what will be recommended by the Germans and French, NC and so on. And for the digital signatures used, for instance, in HTTPS, it will be recommended dilithium. And what is the funny, for the digital signatures of software and hardware or some updates will be recommended hash-based schemes. Concretely, Lighton-McCulley signature scheme and extended Merkle signature scheme. And as we are approaching to the end, I will be more quick now. So this is just the timeline. I already talked about it. Everything will be start in next 2 years, and then there will be like the window of the 5 years when everything should be like transformed to the post-quantum, and after 2030, we will just solely accept the post-quantum solutions. This is the plan of NSA, and I think that also European institutions like ENISA, NC, BSI, and so on will be recommended strongly this. And here we have not exhaustive, but just some examples of the libraries which are already available for you, for developers, which you can use if you would like to add the post-quantum crypto. The most famous is libOQS library. This is the essential library that just was under the Open Quantum Safe project, and I think that a lot of teams and a lot of the, let's say, TELES and OpenSSL libraries use this essential library. But there are like more libraries, and you can also check it in offline in my presentation. And finally, in the last part of my talk, in a few minutes, I will just go through the protocols which are used today and how they should be changed to withstand quantum attacks. So let's start with less known MACsec protocol. MACsec is used on the second layer. It is not very common. I think that several of you maybe heard about it. So MACsec just works with Ethernet frames. Of course, encryption is fine. It is used as 256 long keys. But for the key agreement, there is the Diffie-Hellman or RSA, and there we should use the post-quantum schemes. So some recent works from last 1 or 2 years just started to do the experiments and just to start to implement the post-quantum crypto inside and just try to figure out if MACsec will work with these. The conclusions are good for us. I think, or the researchers think that the MACsec are fine and could be simply moved to quantum safe. What about the IPsec? This is more like widely known. It works on the third layer, and it's used mainly between the routers or maybe between the branches for the building the VPN tunnels. So IPsec is like big protocol, and for the key exchange and authentication, it used the Internet Key Exchange Protocol version 2. And this protocol still like have some cipher suites using the common crypto, but now also some works proved that a lot of these recent candidates are fine for this, except the classic McAleese, because classic McAleese has the huge public keys, which are also like exchanged. So this could be the obstacle for this. So we need to use really efficient schemes which has the smaller keys like lattice-based. And TLS, this is the probably most used the protocol, because TLS is almost everywhere in the internet. It is used in HTTPS, and TLS also use the key exchange and negotiation before the session is built, right? So elliptic car VS8 certificates should be somehow exchanged by the post-quantum certificates, and also there are like a lot of studies that prove that some dilithium or Falcon signature schemes are fine, and even some hybridization also works here. There is only problem with the frames, but if you are using the jumbo phrase, they could like help us for TLS transition to post-quantum. And SSH is also very familiar for you, and it also used the asymmetric crypto, and it is good that the SSH messages are designed to take the big messages which are large enough for post-quantum, and we can simply use everything from post-quantum crypto. Again, McAleese, which using the large keys could be problematic here. And last but not least, I just put in my presentation these main protocols are certificates. And maybe let's certificates, as you know, have the sizes of hundreds bytes, and of course you can use the chain of certificates, which then have the kilobyte sizes, right? And in this picture, there is the proposal where should be some amendments, some modifications in the X.509 certificates format. So you can see that there is a lot of like fields where we should do some modifications and let's say propose some drafts which will be standardized these new certificates and these new formats which will be like ready for carrying the post-quantum cryptography schemes. And let's conclude my talk in the time. So we know now that quantum computers may break current asymmetric cryptography. We know that we need to start to be prepared. We have a couple of years to do that. We already have some standards which are like recommended by NIST and also by NSA and also by BSI and French ANSI. And we know that there is still open topics if we will do just the straight exchange common cryptography by the post-quantum crypto, or we will be more like conservative and we will do the hybrid approach. And for some recent works, we know that already some libraries and security protocol started to be developed and prepared for the quantum safe or quantum era. So that's it. That's my talk. I hope that you bring something interesting from this speech. There is just the references, and thank you for your attention. So I maybe have only just 1-2 quick questions, and then I will be stay here, and we can just talk on the coffee. And so every is here who have the question. Yes.
You said about symmetric encryption, right? That the solution to post-quantum error is to just increase the key length. While Grover's algorithm is polynomial in time, so that the running time would be also increased incrementally.
If I heard you correctly, you ask on the symmetric cryptography, and your question was about if we should just increase the sizes and it will be fine. Yeah, I'm sorry if I not emphasize strongly. Yes, that's the correct. We need only to just increase the sizes, but it is only for the symmetric cryptography. For the asymmetric cryptography, we need to change by the new post-quantum crypto. I hope that's...
Right, but on the slide it said Grover's algorithm runs in O square root n.
Okay.
So if it's polynomial, then increasing the key length wouldn't really change the running time enough, I think, for it to be secure again.
Doubling the key size will not give you the same straight at square root.
Ye-
Yes, wouldn't that make it secure?
Yeah.
Yeah, it will be secure if you just double-sized.
As you would have to keep.
Another question? If not, thank you again, and I think we can proceed with the next talk.
Plug
Yeah,
me.
that's the DevConf.
That's mine.
Yeah.
Was the AppGal to the audience online?
Yeah, it was online, but only the stream from the camera, the capture of the screen that was not working.
Yeah, the slides. But since we directed the camera upwards a bit, it was a discussion.
Hello, everyone. Please welcome Radostin Stoyanov, a second-year PhD student, with a talk, Forensic Analysis of Container Checkpoints.
Hello, everyone. Today we'll be talking about our work with Adrian Weber on introducing container checkpointing in Kubernetes and how we can use this for forensic analysis. There was a talk a few years back at KubeCon introducing forensic container checkpointing and how what are the tools that can be used in production to perform to respond to security incidents and how these tools can be used with containers. And one thing during this talk that was mentioned was that containers don't support snapshotting, and at this time was still in development. And we recently introduced a new feature in Kubernetes that allows you to take a checkpoint of a container. So in this talk, I will first briefly cover what are the security boundaries in Kubernetes, what are the different threat models that we're going to look into, and then I will cover what is container checkpointing and how does it work, and how we can use this to perform forensic analysis, and what are the limitations and some of the future work. So there are two main areas of concern in terms of security for Kubernetes. The first one are the configurable components in Kubernetes, and the second is are essentially the applications that are running in the cluster. In Kubernetes, there are many components running on the control plane node that can be configured, and every node is also running a Kubernetes component called kubelet that is important to be secure. Namespaces are used for isolation between different tenants, and the pods are introducing security context between different containers running on the cluster. And containers isolate applications from the host environment itself. And in addition to that, every application has different network namespace that isolates the communication, different DNS, for example, and Kubernetes also makes available secrets and tokens to the application. And of course, the application is processing sensitive data from users. So the three main threat models that we're going to look into is when an external attacker has access to an application running over the network. In this case, the security controls that are commonly used is to encrypt all network traffic and to use authentication and authorization for all APIs. Another aspect is when an attacker has compromised a container in the cluster or has been able to use a malicious container image to run essentially malicious container on the cluster. So in this case, the attacker can try to escape the container or perform privilege escalation to take over the whole cluster. And the common security controls in this case are essentially limiting the privileges available to containers and limiting the access to the kubelet running on the node, and preventing the applications running in the container from loading kernel modules, and restricting what network access the applications would have. Another threat model is when an attacker has been able to, for example, steal the keys for accessing the Kubernetes API server, so they would be able to create pods and create containers in the cluster itself. And in this case, different security controls that can be used are role-based access control and limiting what a user in Kubernetes can do, and limiting the quotas of resources that can be allocated to a single user. So the problem here is that real-time monitoring systems for Kubernetes don't currently support the ability to take a snapshot of the applications that are running in a container and use this to analyze what has happened during a security incident. And container checkpointing can capture and preserve this state and can be used to analyze what has happened at a specific point in time. But also we need advanced tools to be able to analyze this state. So how do we enable container checkpointing and how to use it? In Kubernetes, there are different pods. There could be multiple pods running on a cluster node, and every pod can have multiple containers inside it, and every container has a process tree, essentially a set of processes running. When the container engine, in this case Cryo, is invoked to perform a checkpoint, then it would essentially call the container runtime, in this case runc, and runc will call Cryo, and Cryo is going to create a snapshot of essentially serialize the runtime state of all processes running within the container. And this state can be used then to restore the container from the point in time when the checkpoint was created, but it could be also used to analyze what were the processes and what files or network sockets have been opened at this particular time. So to enable checkpointing in Kubernetes, Cryo has to be installed on every Kubernetes node. In Cryo version 1.25 was introduced the checkpointing feature, and we currently have a pull request for containerd. Cryo has to be started with the option enable Cryo support, and the container checkpoint feature gate has to be enabled for the kubelet in Kubernetes. And then once this is enabled, you can send a post HTTP request to the kubelet API and specify the namespace, the pod, and the container that needs to be checkpointed. And then this will create a checkpoint, essentially a tar archive that contains all the state of the container in a default location. In this case, varlib kubelet checkpoints, where you can inspect the state further. There is also some discussion about how to optimize essentially the way we store checkpoints, because currently everything is stored in a single directory, and we want to limit the amount of checkpoints that are going to be created for a specific container, just to, if you have periodic checkpointing, to not take the whole disk space available. And for this, we're probably going to create subdirectory or directory for every pod, but it's probably going to come in a future version of Cryo or kubelet. So I have a short demo of how this works. So this Kubernetes cluster with, in this case, just 2 nodes, and we have a pod running a PHP application, in this case, Laravel, and I have a shell script which implements the checkpoint command for kubectl, and this allows me to list what are the different containers and the different pods running on this node. So in this case, we have this Laravel pod, and with a single container called demo running inside it. So this script will send the post request that was shown on the slide, and this will create a checkpoint in the default directory. And in this case, we have 2 checkpoints because I tested this before the talk to see if it works. And we can use a tool we developed called checkpoint control to inspect the state of, essentially to see what is inside of the checkpoint itself. And so this is a high-level overview showing the IP address of the container that was captured, what is the root diff size. And so these are files that have been modified by the application running inside of the container. We can see all these files, included deleted ones. Essentially, this is capturing the read-write layer on top of the container that is used by the application. We can see the checkpoint size and the timestamp, essentially when the checkpoint was created. So we recently introduced this feature that allows us to see what are the mount points. So essentially what has been mounted inside of the container, what are the different processes. So we can see the process ID and essentially the process name, and just a high-level overview of what is captured in the checkpoint. In addition, so if we untar the content of the checkpoint, we can see all the files inside it, and the files or the crew images that the checkpointing tool creates are in the subdirectory called checkpoint. Before this, I'll just show you the content of so the root.fs start diff is essentially are the files that have been modified in the container. We can use a tool called crit or checkpoint restore image tool to essentially decode all the image files, and this allows us to see the details, essentially what is the content of all our checkpoint images. In this case, what we are seeing here is the process tree image, which contains essentially a list of all threads and processes and information about the process identifier, the thread identifier, and other additional information about what is actually running in the what is included in the checkpoint. Here we also have something called ghost files. So these are also known as invisible files. This is essentially when a file has been deleted, but there is an open file descriptor, essentially a file descriptor open for this file. Then this file is also included in the checkpoint, so we can inspect the content of such files. This is also important if we decide to restore the application and see how it will perform, what actions it's going to perform. And there are many different images, and we are currently developing the tools to analyze the state of the checkpoint further. So to go back in my presentation, some of the limitations. These are some of the 3 main limitations that I'm going to focus on today. So the Kubernetes secrets are essentially keys or tokens that are made available to applications running in the container to be able to access resources, for example, database or other services running in the cluster. And when we create the checkpoints, since these will be stored either as environment variables or in memory of the application, these are also captured with the checkpoint, which means it is important to keep the checkpoints secure so that we can prevent leaking information about sensitive data such as keys. In the case of live migration and fault tolerance, we would want to keep this information in the checkpoint because we can use the checkpoints to recover the application from failure or to move it to a different physical machine. In the case of fast startup, this is when we want to optimize to improve the startup time of applications by taking a checkpoint immediately after some index or data has been loaded in memory. And starting the application from checkpoint will essentially improve the startup time. In this case, we don't want to keep the secrets or passwords stored in memory because we want to essentially initialize every application with different key. So in this case, we need some techniques or methods to be able to remove this secret information from the checkpoint. Another limitation is when an attacker can essentially perform different actions that would make it more difficult to understand what was actually happening in the container, or mimicking the behavior of trusted processes, essentially using existing processes within the container that would make it more difficult to understand, for example, what was actually happening during the attack. And an attacker can also perform a set of actions that are not related to the attack itself, and this would also make it more difficult for example, intrusion detection systems to detect this attack. And there are certain cases that CRU doesn't support. So, for example, certain system calls are not supported, or certain network sockets or nested namespaces are essentially features that CRU doesn't support. So if an attacker wants to prevent the checkpoint from being created, then they could use this type of techniques to prevent the checkpoint. And some future work. So how can we use container checkpoints with intrusion detection systems, and how this can be used for preventing attacks? There are different aspects that can be used from checkpoints. One is to improve the visibility of tools such as Falco to be able to see what is actually running in a container, but also to use this for further forensic analysis after a security incident has occurred. Container checkpoints can also be used to detect certain actions and trigger an alarm. And a new restart policy can be introduced for containers to allow to restart from a checkpoint. And potential attacks that can be used to inspect with checkpoints are, for example, SQL injection. We can detect when certain behavior is happening in the container, and it's the same with command line execution, or when an attacker is using a file inclusion attack. And when a malicious container has been is currently running on the cluster, we can use container checkpoints to detect and improve the monitoring of the system, and introduce security policies that would allow us to detect different incidents. And finally, I just want to mention about two Google Summer Code participants who are currently working on this project and have been contributing to this work. And thank you very much, and I'll be happy to answer any questions.
Have I understood it correctly that you can decide while taking checkpoint if the secrets will be included or not?
So this is something we have been discussing in the community, what would be the best approach of doing this.
So it's not implemented yet?
Yes. The way we discuss about implementing it is to introduce a signal handling. So we can send a signal to the application running in the container, and then the application has to essentially drop the secrets. There is another project implementing checkpoint restore for Java applications. They essentially perform certain actions before the checkpoint, and then certain actions after the checkpoints, which can help with this as well.
So some listeners, and it can be triggered by triggering the Kubernetes checkpoint. It will trigger inside the Java application this.
Yeah, but it's still in development. It's still something that we are working on.
Thanks.
Yeah.
Is the idea to at some point, maybe it is, and I missed the part, it is the idea that at some point we have like regular checkpoints, not let's say ad hoc, because now I need a checkpoint, but we have that checkpoints logged, so we can check them after an incident.
Yes. So after, just to repeat the question, can we have a log that would list all the checkpoints and then use the checkpoints after an incident has occurred? And yes, a checkpoint would allow you to not only see what was actually happening in the container, but for example, if an attacker runs something entirely in memory without touching the disk, which is something that is commonly used today, you can use memory forensics, or essentially see what was the memory content inside of the checkpoint and understand what was the attack. Yes?
So I'm not sure if you mentioned, but I was wondering how much overhead does checkpoint in terms of how much space it's taking on the disk once you create it. So I guess it's dependent on the size of the container and so on, but how much overhead does the overall crew mechanism generate?
Yeah, crew is very optimized. So the way it works is using the ptrace system code to enter the address space of the process, and then use essentially create a Unix socket with the crew running outside, and using splice, which is essentially avoiding copying the memory from the process into a set of files. So it's very efficient. But of course, it depends on the size of the, for example, how much memory does the container use. Then we have to save all this state. Yes?
Yeah, so if I understand correctly, you should have some faster permissions in order to create this checkpoint, right? Can I do the same with some limited permissions like ordinary user or even less?
Yeah, so essentially it's, I think you need admin permissions at the moment, and essentially you're sending HTTP request to the kubelet running on the node. So essentially you just need to be authorized to perform the checkpoint. But if you can create a checkpoint of a container, then you have access to all the memory of that container. So it's, it has to require admin privileges. Yes?
Can you use checkpoint from an outer part so that you can check the containers one after the other simultaneously?
Yes. Can we checkpoint the containers one after the other? Was that your question?
Yes. How
Yes. So this is actually something that we're working on. It's essentially, how we can synchronize the checkpoints between different containers. So we're introducing essentially a synchronization mechanism that allows to create the checkpoints of two containers at the same time. Or if these containers are running on different nodes, to synchronize the checkpointing between different containers. This essentially if you have a distributed application running on multiple nodes in the cluster. Thank you. Thank you everyone, and is that
Objective, it's easy, right? So,
okay, we can start.
Okay. Hello everyone, and thank you for coming to our slot today with Karm. My name is Christos. We will talk about our joint work with Red Hat in the Aero project. I have, as you see, a couple of jobs. The main one for this talk is that I'm coordinating technically the Aero project. So, Karm with me.
hello, I'm Karm. I work as a quality engineer at Red Hat on making Quarkus compilable to native image. Over to you.
Thank you. So let's start a little bit. So in this presentation, we're going to start talking about European policy and going to go down to compilers. So it's going to be a rough ride, but stay with us. So what is all about? The whole story about how the European Commission sees the sovereignty of the European Union regarding chip manufacturing started, I would say, more or less along with the pandemic and the fact that the majority of the chip manufacturing in the world is concentrated in Taiwan. To solve these problems, both the US and the EU, they put forward legislation in order to create sovereignty. So what it means? So the European Commission, in particular, they voted the European Chips Act, which is a 50 billion euro budget project in order for the Union to be able to design, manufacture, fabricate, and procure processors made in the EU, let's say, which is a big task. It's a big task, and it requires a lot of investment, both from individual countries and also from the Commission. After this was voted, which was, let's say, a couple of months ago, in parallel, the European Union was already starting the prep work. So what it means, projects in order to build both the hardware and the software. And as part of this collection of different hardware and software, it is our project, which is called the Aero. So the goal of the Aero is to create, optimize the software stack of a typical cloud application stack, like the Docker Kubernetes, different runtimes, and operating systems, in order to be ready when the hardware of these EU processors will go into market. So essentially, imagine that there are projects building the hardware and the software working in parallel, and at some point in the near future, hopefully, we're going to be able to use these projects, or at least the outcome of these projects, in order to run and help companies within the EU to migrate from Amazon or Azure to these cloud services. And in particular, in this Aero project, we are many partners, and the idea is that we're trying to get a collection of software frameworks that exist on current cloud deployments and optimize them. And this hardware ecosystem is going to be very heterogeneous. It's going to be cores with accelerators inside, in the SoCs, and accelerators like GPUs and FPGAs connected around these cloud services. And we try to optimize compilers and runtimes and different frameworks for managing cloud operations. And of course, it's a small project. We cannot solve all the software, but it's a good start to have a first implementation that makes sense for somebody to use these EU cloud services. So what is this hardware? We don't know. I mean, we know, but not exactly. So what we don't know? We know that there are many projects of creating different designs. So there are projects under the umbrella which is called the European Processor Initiative, which creates different designs of cores, of accelerators, of interconnections, packagings, and these designs, they are being funneled to other projects like ours, where we take those test beds and we start bringing up the software. So if you go to the European Processor Initiative website, you're going to see many different streams. Chips for HPC, chips for automotive, for IoT. Some of them are ARM-based, some of them are RISC-V-based. So it depends the project, they experiment with different designs. But nevertheless, no matter which design somebody will choose, at some point we will have to run and prove its performance. We are not involved in the hardware design. We are, let's say, the consumers of these hardware designs where we bring the software. So our target, it is a hybrid of ARM and RISC-V, which is the first commercially available processor from the EPI project, which is from a French company called Cyperl, which is the RIA processor, which is an ARM core. Inside, they put some RISC-V accelerators, and then you have PCI Express connected GPUs from Intel and NVIDIA. And of course, we have other, let's say, FPGAs to experiment with more, let's say, research stuff compared to current upstream software. I cannot talk about, I don't have time at least to talk about the whole software we target, so I'm trying to narrow down the discussion to managed programming models and runtimes, which is University of Manchester and Red Hat's, let's say, expertise. As you see, here is the whole stack that we try to cover. And regarding the runtimes, we target managed programming language like the JVM. So although my talk is called Java, in reality, it's JVM. So anything that runs on top of the JVM will benefit from this work. And we target Java and frameworks for microservices and Tornado VM for accelerating Java or the JVM applications on GPUs and FPGAs. And of course, we have the other stream for native programming languages like SQL and DPC++ and OneAPI, which is done by Codeplay and Intel in this project. So now I'm going one layer down the abstraction, and I will narrow down the discussion about the Java or the JVM. So what do we do in this project? Normally, we try to optimize two main frameworks. Of course, we have the OpenJDK distributions that they now have RISC-V backports from Alibaba, and they already have ARM support, and Red Hat is doing a great work supporting the ARM builds. And these are all, let's say, more or less upstream, and people can download and use them. And now we take it a step further, let's say, at least in our project, to try to experiment with this hybrid ARM RISC-V and accelerators. So how this would look like for the developers and for the hardware. And we focus on Quarkus, which will be the part of the talk from Karm, and Tornado VM. Tornado VM is a framework, probably you haven't heard of it. It's a framework from the University of Manchester, where we're trying to, let's say, bring higher performance through heterogeneous execution on the JVM. So what is Tornado VM? In a sentence, it is a JVM plugin. Although it's called VM, it's not a new VM. Tornado VM by itself doesn't run anything. It needs a host JVM. So it is a plugin. So you have, let's say, Amazon Corretto or Mandrel from Red Hat or OpenJDK. You download it, you plug in Tornado, and it gives you a lightweight API which you can use to accelerate automatically code on GPUs and FPGAs. And I will show you later a little bit how. So essentially, it is an add-on on any virtual machine JVM that supports JVM CI that we can use to accelerate automatically code on accelerators. And it has, let's say, two main features that we advertise. The first one is, of course, the API. So you don't have to do a lot of work. If you have done GPU programming, currently you have to use JNI calls and CUDA kernels and do the memory management, manually copying data from the Java heap to the actual accelerator. So Tornado VM solves all this problem. Tornado VM does not expose any hardware to the developer. So we are very strong believers of the original Java idea that you write once and you run everywhere. And for us, this everywhere is not only multi-ISA CPUs, but also GPUs and any platform or modern hardware platform that exists. And of course, we have the automatic code specialization. Now, if we run, for example, OpenJDK on ARM or Intel, the compiler, the C2 or the ground compiler, whatever we use, will have a specific compilation chain, and underneath we have the intrinsics, so each company goes and puts their own specialization. This is what Tornado VM does also. If you compile your code for GPUs, it's going to be different. If you compile your code for Intel GPUs, it's going to be different than NVIDIA. So we detect all those hardware, and automatically we specialize the code to run better on each platform. So how do we do it? Essentially, we plug into existing JVM, in that case OpenJDK, so developers can use our API, and then we take the bytecodes, we go through ground compiler, we do the IR, and then we lower either to OpenCL, or PTX for CUDA, or SPIR-V for Level 0. And each of those frameworks can target different kind of devices. And on the top on the right, we have different kind of distributions we support and different kinds of hardware vendors that we support. I cannot, again, I would like to spend at least 6 hours talking about Tornado VMs, but I cannot. So I will try to give a small, let's say, idea of what is the model we use. So in any GPU programming model, essentially, we have to do 2 or 3 things, depending how we look at it. The first one is we have to copy the data from the CPU memory to the accelerator memory. We have to run the code there, the kernel, the CUDA or OpenCL, whatever, and then we have to copy the data back from the GPU's memory back to the Java heap. And this, let's say, execution model, it is really simple to comprehend. I have to do 3 things, no problem. But in the JVM world, these 3 things require a lot of code that you have to do manually. So we solve these problems by automating everything that the developer shouldn't care about. How? By having essentially 2 types of code in the API of Tornado. The first one is the host code, the controller who does the playmaking, which data is going to go where, how, and all these optimizations. And the second one is the compiler will generate the kernel or the code that corresponds to our Java method for acceleration. And we have the task graph here, which is essentially the structure that we compose different tasks. So in that case, we have a method called method day in class, right? So it's just like a Lambda function. So we don't change the Java code, we just pass it there, and the compiler will piggyback on some annotations we put, and then it will compile it and run it complete transparently to us. So there's no GNI or any manual work that have to be done. Now, we have 2 APIs for development. We call the loop parallel API and the kernel API. These are complementary. The loop parallel API, it is more for, if you have a for loop, let's say I have a for loop that it's very heavy and I want to accelerate it, you just put an annotation and then we do it automatically. But if you're a power user, so if you come from CUDA and you want to put your barriers, your local memory, all those GPU stuff inside, you can use the more advanced kernel API. So I make everything sounds perfect, right? Tornado VM is going to solve our problems. Is it? No. Why? Because we have to know when to use it. Not all applications require the raw power of a GPU. Only some of them, they require it. For example, some use cases we have are computer vision, ray tracing, machine learning, and face detection. As soon as we have a lot of compute, a lot of parallel computation and data to process, then I think it makes sense to consider GPU acceleration. And Tornado VM, it's, in our opinion, one of the easiest way to achieve that. So I would like to conclude now by, hopefully, showing the ray tracing demo running. We just ported it from Linux to ARM MacBook, so I cannot guarantee that it will run. Okay, so what do we have here? This is a scene written full in Java. There is no C code here, okay? This is full in Java that does ray tracing. So it renders in real time on the CPU, on a single thread, at 1-2 FPS, okay? So if I go here and I try to zoom, it's very choppy, because now the CPU now is struggling, now it's working full. And if I zoom now, you could see the shadows, the reflection of the light source on the rays on each ball. So this is not real time, this is useless. And you can ask me why you write this. So I'll show you in a second. So let's change implementation. Let's go from pure Java single-threaded to another Java implementation that uses parallel streams. Now, I'm around 10 FPS, because this is a 10-core machine. I can scale out on the machine, and now it's easier for me to zoom in. Before I was zooming in, but you couldn't see because it was moving like a turtle. So let's now go GPU. So now, the 4 magics happened. The first magic, it didn't crash, okay? The second, hey, The second magic we see here, now the same Java code. This is the same Java code that was running on single threaded. Tornado VM took it, compiled it to OpenCL, and ran it on the M1 Pro GPU, which is a really powerful one for the record. And now we are at 60 FPS. And now we can actually start. It's real time. You can zoom in, zoom out. And also, you can change the different shadows and reflection bounces. The more we change them, the more heavy it becomes. So again, this is pure Java code, automatically compiled to OpenCL, running on the GPU. Third miracle is that now all the computation happens on the GPU, so the CPU is sitting idle. So let's develop a physics engine on the CPU. Run the rendering on the GPU, the physics engine on the CPU. So now, all this physics engine here, you see all these balls that are bouncing, this all code is implemented on the CPU. The GPU does the rendering. The fourth magic, that I didn't have to stop the application. I can change now the Java code between running on the CPU, running on the GPU, make combination while the application is running. And this is, I would say, the strength of Tornado VM, which is called dynamic configuration. And this is where the VM comes inside. Tornado VM internally has its own bytecodes that can recompile the code for GPU or CPU the same way that the OpenJDK or any JVM compiles the code between C1 and C2 without stopping the code. So we follow the same ideas, but this time for heterogeneity. And I think my time is up. Thank you very much, and I pass the microphone to Karm to talk about the beautiful Quarkus.
This is the fourth miracle, whether we managed to switch the displays, and whether my setup survives it. Wow. Hello, 111. I will be talking about Quarkus, which is a Java framework. It's a part of the Aero project, and it's a suite of libraries that are tailored to be cloud native. And in our context, that means being very small, also in the footprint and in the resources consumption. I'll be dropping some buzzwords. So I don't know who's in the audience. Like if I say hibernate, does it ring any bells here? Okay, a couple of them. Spring, some Java libraries. Okay, so this is Java on the server side, like building Java applications mostly on the server side. GraalVM, it's JDK, a custom JDK with custom JIT and capabilities to compile various languages in a native executable. Mandrel, that's what our team is focusing on. It's a distribution of GraalVM, which is made smaller because it focuses only on Java. It doesn't deal with other languages. And its main differentiator is that it uses Temurin JDK as its base, and it adds the native image tool to it. So while you are using Mandrel, you are using the Temurin JDK you would download from Adoptium without any additional patches. So native image is the tool we'll be talking about today. It compiles the suite of your libraries in Quarkus in your application into a native executable. So you can have your Java application that uses several databases, has database drivers, it talks to Elasticsearch, it's got a lot of stuff going on, a lot of dependencies, and native image will choose through all of that, construct some kind of a closed world with all your dependencies, and compile that into a native executable, including all resources, all additional files. It's all going to be baked in a single executable. This closed world assumption is an important stone in this whole machine because sometimes you need to specify that you are going to do at runtime something that is not apparent from your source code, but Quarkus helps you with that and does this heavy lifting for you. So for instance, if a library, let's say Elasticsearch, is doing something at runtime that it's not apparent at build time, there is a Quarkus extension you depend on, and this Quarkus extension recognizes it, constructs bytecode for it, and then it's ready for the compilation. So you can compile things in your native executable that wouldn't be surprised at runtime by a missing, let's say, class. I will jump right into trying it out on an ARM server. Hopefully, we are now. We are now connected to Ampere Ultra 80-core ARM server. I got Jenkins running there, and we will build Quarkus application. I got downloaded JDK, but not our native image, not the compiler, because that's going to be used from container image. While it does its thing, I will continue with slides and then come back to it. Quarkus is a huge suite of extensions. So while your end application is trimmed to the bare minimum and the footprint is as small as possible, the possibilities of all libraries are really huge. And many of them package some native code in the jar files. And that comes pertinent to making sure that things run on ARM, because not all of those libraries produce ARM binaries with them. And there is some example of all the libraries that in the core Quarkus got some native dependencies, and there are some of them that don't currently produce ARM binaries. Those are usually loaded with Java native interface and have some Java fallback. So currently Quarkus runs on ARM, but there is still a lot of stuff that could be done to make it better. This compiler I talked about, the Mandrel distribution of GraalVM, can be downloaded from our GitHub site, where we got ARM binaries for Linux. And we also produce container images, so you don't have to install it on your system. You can just get the Temurin JDK with the native image compiler from the container, and that's what the Quarkus framework does for you also. So as a Java developer, you can tell Quarkus, okay, I've got my application as a Java developer I'm used to. Compile it to native image for me. I don't know what's native image. I don't know what's GraalVM, and I kind of don't care. I want my application to be compiled to native executable, and Quarkus downloads that container image, uses Docker or Podman, and compiles it for you. So there is a lot of testing involved to make sure that Quarkus is gradually more and more ready for ARM. We use various integration test suites for that. Some of those are tiny specialized apps or reproducers targeted at some special features. Some of them are huge suites, or let's say Quarkus integration test suite. And some of them are kind of artificial applications that jam a lot of stuff on top of each other to really stress the compiler that it could handle a lot of generated entities on Hibernate or stuff like that, and that it wouldn't blow up and it would handle it. You can build Mandrel yourself, and it's not a joke. It's not any kind of like obscure one of those projects you cannot compile when you download them. The compilation scripts are written in Java using JBank, and you can run it. You just give it Java home to Temurin JDK, GraalVM GitHub repo, and it compiles the native image compiler for you, the distribution. We got public-facing Jenkins, where we got these ARM servers connected, where we build and test periodically on various branches. So that's our public-facing driver. And these are our precious loved ones, our two bare metal servers we are currently most working with. They are photographed on my desk, but right now they are safely in a data center. David looks like he doesn't trust me, but it's really already gone. It's not there anymore on the desk. Those were donated by ARM to make this effort accelerated, and it's part of the Aero effort we are doing. And they've got the same Neoverse N1 architecture as the current Aero spec or the target. They are quite beefy machines with 80 cores. The compilation I started is done, and the Quarkus is running. So I will just scroll back to see what took place. I started. I downloaded Start with Quarkus like demo project, unpacked it, and just run Maven. That's all that happened in this Quarkus application. And it compiled the Java bits, it compiled Java bytecode, and then it realized that I'm trying to do a native image build, and that I don't have any native image or GraalVM Mandrel compiler on this system, on the path. So it resulted to check in whether I have Docker or Podman installed. It found I got Podman on the server. So it used Podman to download Mandrel builder image, which is one of the artifacts we are regularly updating and pushing to publicly accessible container registry. And it downloaded that image. It was already downloaded on the system. And the horrendous blob of text, it was constructed automatically by Quarkus for you to drive the compilation of your application to the native executable. So that was generated by Quarkus. It realized what your application needs to be properly compiled to a native executable, and that process started. The reason why I kind of sneakily alt-tabbed elsewhere was that the compilation is by no means instantaneous. It takes some time. It analyzes the classes in the closed world. It analyzes whether there is any GNI access, and it finally got the executable image with machine code that also contains baked-in resources. So, for instance, if you got some properties files in your jar files or something like that, that's all going to be packed in one single executable. And it took 40 seconds to build. And the Quarkus is running now, and I can access its default web page for this one particular demo application. The same binary, literally the same I built there, can be run also on my phone. I don't know how to connect it to the projector, but it runs there. It runs Debian. And Quarkus starts there in 52 milliseconds. To assess the state of things and to gradually make them better, we are collecting metrics about build time and the runtime. Build time is what I showed here, how long it took to compile the application. Bigger the application, bigger your closed world, the longer it takes, or could take. So that's one of the things we are looking at, and also the runtime. So that's how the application behaves when it runs. We've got a collector for that, a tool written in Java using Quarkus. The reason why I mentioned that is that I don't have any Java installed on my server. I build the application in GitHub Actions, and I just push the executable to the server. So there is a huge, rich Java application talking to database running on the server, but the server doesn't have any kind of JVM installed on it. This is how we assess the build time metrics, and this is an example of some of them that are collected. The most important would be how long it took in all to compile an application. And also it's important what's the target architecture. Runtime matrices are more interesting. There is a rough comparison of the same application that uses a lot of microprofile libraries. In Hotspot, it takes much more memory to run. And in native image, it's much more memory efficient. The reason for that is that it doesn't have to keep a lot of metadata for a lot of stuff, because there is no just-in-time compilation, there is no de-optimization. It just fixed what's compiled in the binary, so there is a lot of stuff that's not needed at the runtime. And it also starts quicker. That's not only thanks to the native compilation, but it's also thanks to Quarkus that pre-initializes a lot of stuff and bakes it on the heap. I ran through that pretty quickly, but we agreed to leave 5 minutes before the end for questions. So we can go back, both of us, to anything that caught your eye or that you find weird or suspicious and you would like to heckle us about or ask about. So shoot. Oh, dead silence. The question was whether Tornado VM is using only public JDK APIs or whether there is anything to be proposed to the whole JDK ecosystem. Take the floor.
The answer is yes in both of the questions. So at the moment, we are using normal Java APIs, so two things. First, we use normal Java APIs. The JVM has to be JVM CI compatible, so it has to support the interface. But as soon as we go to Tornado VM, as soon as we go GPUs, the Java spec doesn't apply anymore, because that's parallelism. As soon as you go to parallel computations, then you cannot guarantee consistency or ordering any. But as Tornado VM improves, we would like to propose to the committee some changes that would help benefit Tornado VM, specifically for native data types and the Panama integration. More questions?
You've got one early quitter.
Okay.
I would hear a hairpin drop in this room. So they are either like stunned how awesome it was, or didn't understand, or I don't know.
Okay,
good.
Please.
If there's no more questions, then thank you very much.
Thank you very much.
Thank you.
Okay, so hi everyone, welcome to my talk. So today I'll be speaking about future of artificial intelligence and machine learning in software testing. But before starting with that, I wanted to introduce myself first. I am Shreya Asthana, working as a senior software quality engineer with Red Hat, and it's been around 2.5 years since I'm with Red Hat. So I have been involved in many testing tools like Selenium, Cypress, Lemon Cheesecake, including the language Java, JavaScript, Python, and so on. Apart from this, I also do have some techno-functional skill related to the ERP application like Workday and Oracle Cloud. So that's pretty much about myself. Let's start with the presentation. Okay, so this is the agenda. So we will talk about what exactly the AI, ML, and the deep learning is. We will talk about AI history, why we need the AI in software testing, the problem, the solution, the tool, what is going to be happen at the back end of AI-based testing tool, benefits and the challenges of AI, and AI current application. So let's begin with the presentation. Okay, so this is the picture which having, relationship between the AI, machine learning, and the deep learning. So AI is the development of computer system that performs the task which typically requires the human intelligence, such as recognition of speech, recognition of image, and understanding the natural languages. And also AI is having, it is a broader field that contains the many subfields like machine learning, deep learning. So let's talk about what exactly the machine learning is. Machine learning is all about training the computer algorithm so that it can find out the patterns from the data. And it's basically the main aim is to create a model that can identify the pattern and can make a prediction and the decision based upon the data that they haven't seen before. Now next is what is deep learning. Deep learning uses a neural network and it performs the task which is a little complex like recognition of image and speech. Apart from this also it simulates exactly the same way as the human brain works. So this is all about AI, machine learning, and deep learning. Okay, so in this particular slide we will see how AI came into the picture and how it transformed into the different, the different sectors. So I have divided this slide into the 3 generations: first generation, second generation, and the third one. So first one is all about large data set. So in the online fraud detection and suspension, AI worked on analyzing the history of users, and also it analyzed the history just to provide the risk rule. And user can also create the risk rule by allowing and blocking some user section. And also the users can flag fraud and the non-fraud activity so as to provide so as to avoid the false positive and to provide the better risk solution. Now let's see how AI help in the supply chain management. AI help in the supply chain management by it help in telling the accurate inventory management. It helps in predicting the demand. It helps in understanding or letting the users know the shortage and the excess of an asset in the store at given point of time. Now let's talk about the second generation. So second generation is all about studying about the human being. So while studying the human data, AI created social media platform and the recommendation system. So creating a smaller recommendation system was a easy challenge, but creating a big recommendation system which can handle millions of users and millions of data was a massive development in the terms of AI. Now let's move to the third generation. So now third generation is all about creating a machine that can mimic a human being. but I can say that we are still very far away from the true humanoid. Now the question is, what is next after 2020? So basically, what is next after 2020 related to the software testing world, right? So before starting with, why we need, let's understand, how AI help in the software testing. Let's see why even we need it, right? So AI automation needs sustainability. It means that your automation script needs to be sustainable, it needs to be maintained, it needs to be refactored, and it needs the same attention as the business-related code. Decrease the maintenance effort, it means like maintenance is time-consuming and it is costly. So this can also be the challenge of implementing the software testing without the AI. Now the third is root cause analysis is a time-consuming and annoying. I completely agree with this, because let's take an example that your test cases are running in the CI pipeline and your report got generated. And once you open the report, you saw that many of the test cases, or you can say, 50% of the test cases are failing due to the same reason, right? So why we need to invest our time in fixing same failure for so many test cases, right? So these are the challenges which I saw we have right now having in the software testing without implementing the AI. So I started doing some research and got to know that there is a survey which tells us that 75% of the test automation scripts are failing due to either bad locator strategy and locator change. So this is the problem which I identify. Let's move to the solution, but before moving to the solution, let's talk a little more about the problem. Okay, so now what exactly the problem is? Yeah, so problem is unable to locate element. That is exception, no such element. Okay, I think many of you have already, familiar with this exception, but still I wanted to explain a little more about it. So what exactly the no such element exception is? This kind of exception occur while you're creating a UI test cases, and it happens when there is an application change and the locator change or any property that has been changed for a specific application. So now what is the solution? Solution is the self-healing in the test automation. So self-healing in the test automation is one of the technique that has been provided by the AI-based testing tool. We can see that nowadays we have a lot of tool in the market which is based upon the AI. I mean the AI-based testing tool. So the user might be confused to choose one of them according to their requirement, right? So, but before seeing the tool, let's understand what exactly the self-healing is. It is an automation of an automation. So you have an automation and there is some change that has been application, I can say application change. So what AI-based testing tool do is it heal your automation script. Like it creates the automation based upon your automation framework. So that is why it is called the automation of an automation. Okay, so now it is based upon the AI algorithm. So I mean, this will going to be talked little more detail in the later slide. It stores the information about the application. So it means that your AI-based testing tool stores the application, about your system, and about your objects. Test heals the automation script. We have already saw that. It helps in reducing the maintenance. So yeah, it helps in reducing the manual effort, which can reduce the cost and which can reduce the time which involved in doing the manual task. So this is all about the self-healing which is provided by the AI-based testing tool. So we have a lot of tool in the market that I have already told, and it is quite confusing for the users to choose one of them. So don't worry about that. I'm not going to share the one of the best tool, but we will going to talk about how many tools we have in the market. So we have the Mabel, we have Testim, we have Tricentis, and we have Selenium. So I'll take or maybe pick one of the testing tool in order to let you all understand how the AI-based testing tool work. So I just chose Selenium. It is random, not any biasing, you know. Okay, so Selenium. Let's talk a little about what exactly the Selenium is. It is an open source. It is based upon the Selenium and Java. So it is having a prerequisite that if your test cases is Selenium, and if you're writing the test cases on the Selenium, and the Java, this is a prerequisite. And also, like if you're using Selenium and Python, then you have to use Selenium proxy. Real-time engine. So it doesn't require to install on any server. It just tied up with your test cases and it runs automatically. So installation is very easy. Integration is very easy. So next point is integration. So we just spoke about it. Integration is very easy. Machine learning algorithm. So behind the AI-based testing model or tool, there is a machine learning algorithm which is running. And it provides you the solution, right? Integration done on the WebDriver IO. So in the image, you can see that I have created a Chrome driver, and with the object of Chrome driver, I have tied up self-healing driver. So this is how that you have to integrate your Selenium object with your Chrome driver. So it is very easy to set up. So now I have chosen an Selenium to let you all understand how the AI-based testing tool work. Okay, so this is an example which I have prepared for you all. The monitor is considered as your test framework. We have a Selenium jar, we have a Selenium backend, and we have a UI on which we will going to do the automation. So in the normal scenario, what happens is when you write your script, it try to find the element. Okay, so we will try to automate the password. Password is having an ID mp password 1, and your automation is also having find by ID by mp password 1. So till then we are good to go. So what happened is your framework will going to find this element on the UI, and UI respond that okay, cool, element found. So now what exactly happened when Selenium come into the picture? Your script, your framework interact with Selenium jar, and it tells the Selenium jar that we found this locator successfully. And now further, Selenium jar will interact with the Selenium backend, and it will save the locator which is there on the UI, which is running successfully. This is the regular scenario. Now, one climax come into the picture. We have a version, new version, and related to the naming convention of an attribute ID. So now, your application password field ID is changed from mp password 1 to password. Now in the regular scenario, what happened is you go to your script and you keep on changing the locator. Let's suppose if you have a 50 locator changes, then you have to do the same task 50 times, right? You will go your page object and you will, locator file, and you will change the object 50 times. So, but now you don't have to be worried about that because we have a Selenium in the picture. Now, what exactly Selenium will do is, okay, your ID is changed to the password. Now, what Selenium will do is it again try to find the element, and without the Selenium, it will try to find the element, and it will say that no such exception, which we have already saw that if there is a kind of locator change, then these kind of exception come. I think testers must be familiar with this kind of exception, that we have to go through this exception quite frequently. Okay, so once this exception came, what our automation script do is, it again interact with Selenium jar. It tells the Selenium jar that, oh no, this time we are unable to find the locator. So now what Selenium jars do, Selenium jar again interact with, Selenium backend, and it tells the page state. And now the next thing which happened is between the Selenium jar and the Selenium backend. So between these two, there is a AI algorithm which work. They work the AI algorithm, and Selenium produce a new locator. And this new locator is called the healed locator. And this Selenium jar, provide this healed locator to your script. And inside the script, you can see that ID is now being upgraded to password. Okay, so now manual intervention is cut. And now it again try to find the element, and the element found. So this is the architecture that has been set up behind the AI-based testing tool. Okay, so we have talked about the problem, the solution, the tool. Let's talk a little about benefits and the challenges that we have for using these kind of AI-based testing tool. So it improves the test coverage. So AI analyze a billion amount of data, and while analyzing those data, it find the defect that may go undetected while doing the testing, So that is why it increased the test automation coverage, and it also try to decrease the risk of rate of risk, which might be, slipping through the cracks. Faster, so its execution is very fast. The defect detection is accurate, and it also have a test plan and the execution, which is quite better. Self-healing, I think that this we have already saw that it's self-heal. It provides one of the mechanism which is a self-healing. Predictive analysis. Okay, so while analyzing the data, or while fetching the data, AI predict the a future potential issue, and it delivers the same to the testing team, so that a testing team might be alert before it can, be the bigger problem while doing the release and so. And also it provides the big data insight to optimize the testing strategy. So these are the, benefit which I saw by using the AI-based testing tool. Now let's see the challenges of using the AI-based testing tool. So it requires the specialized skill and the expertise to handle these kind of tool, and it related to the infrastructure and resource. So AI is computationally very expensive, and it is estimated that to implement a AI model, it is getting doubled every 3.5 months from 2012 to 2080. Maybe that is why it has been used by the big giant company only. Difficult in choosing the right tool, that we already saw that we have so many tools in the market. So it could be quite difficult in choosing the tool which is right for you. Data management and quality. So AI produce a sample data, but before going to the production, it requires the high quality data. Else developer has, maybe has a risk to garbage in and garbage out. So this could also be the challenge, and the security and the privacy concern. So I think this is a very, very much important, because if I talk about the organization, so it could be possible that organization doesn't want to share their data, right? And we know that AI-based testing tool fetch or stores your application data, your system data, your object data. That might be the security risk for any organization. So this is the biggest challenge for using the AI-based testing tool. So we saw the benefit, challenges. Now the current application, virtual assistant. So we will talk about how the AI is been, used by the other different, industries. So in order to use in the virtual assistant like Google, Alexa, Siri, these are using the AI algorithm to understand the human command and to provide the information and to perform the task. This is how it has been used in the virtual assistant. Recommendation system. So like Netflix, Amazon, Spotify, what these are doing is these are fetching the human data and it try to stores the preferences about the human, and according to that preferences, it suggests or recommend you the song, the movie, the product. So this is how it has been used in the recommendation system as well. Autonomous vehicle. So company like Tesla, these are using the AI, deep learning, and the other algorithm to create a self-driving car. So what does the self-driving car do is, at the back end, they are also using the deep learning, machine learning, and so many complex things, to understand the surrounding. And on the basis of that surrounding, they take a decision that is a driving decision. Natural language processing. So AI-powered natural language processing, like your Google Translator, your chatbot, these are also, again, using the AI algorithm, AI, ML, and the deep learning. Fraud detection. So while analyzing a large amount of data, AI categorizes the fraud and the non-fraud activity by analyzing 1 million data. So for this also, AI can prevent your fraud detection. Example is if you are using your banking phone and it captures your live location, that on this location, you usually log in your internet banking or something like that. But if you log in through some other country or some other location, it send you the email or maybe the text that on this location, it is trying to log in into your internet banking. Is it you or not? That is mean that at the back end, AI is storing your information about how you do the things. Basically, it categorizes fraud and the non-fraud activity. So it is also helping in detecting the fraud activity. Healthcare diagnosis. So AI now is been used in the healthcare industry as well. So it used in analyzing the X-ray, analyzing MRI, analyzing CT scan in order to find out the different diseases like cancers and other anomalies. So it also helped the radiologist in their diagnosis. Personalized advertisement. So personalized advertisement like Facebook advertisement, Google advertisement, these are targeting the advertising campaign, and according to the user preferences, they are suggesting, the advertisement. Financial trading. So AI algorithm also help in analyzing the news, analyzing the financial data, and in order to track or maybe to help in detecting the stock market or something. So that is why it is used in financial trading as well. The last one is customer service chatbot. I think nowadays many organizations are using this customer service chatbot in order to cut down the manual intervention, in order to provide common query and the instant customer support. So these are the different industry you can see nowadays are using AI. So before ending my presentation, I wanted to share one thing with you all. While creating this presentation, one constant question was running into my mind. And that question was, will AI going to replace software engineers? So anybody in the room who is having the same kind of question like me, maybe they can raise your hand. Okay, pretty much I think, okay. So according to me, I think this will never going to happen because in 1977 or 1978, there was a thing called program generator that came into the picture, and people were saying that this will going to take away all youngsters' job. But this never happened. You know the reason behind it? So the reason behind it is a human brain. I think it is so flexible and so compatible, and it adopts the things so quickly that nothing can replace the human brain. So what happened is people started solving the bigger and bigger problem, which these AI or this program generator were unable to handle it. And so that is why AI, ML, so deep learning, these are good. We should welcome it. We can consider this as a base, and on that base we can show our creativity, we can show our smartness, we can show our innovation. So with that positive note, I am done with my presentation. Let's move to the Q&A. Anybody's having any question? Yeah.
Yeah, so if element will deleted from the page, not changed, Selenium will notice it?
If nothing you have changed on the page.
No, if some element was deleted on the page, not changed it.
Yeah, so it will going to handle that thing also. It can, give you a notification or sort of message that this particular thing has been changed, because anyhow, AI analyze your attribute, this which is attached to the element, and if there is some change, edit, delete, or add, it will going to alert the user, and accordingly it will modify. Because in your current code or maybe current test automation script, you have not written that particular field, or you are not using that particular attribute, obviously it will not going to add that in your framework, because might be that it is not a functional test that you want to do, right? But still, this will going to alert the user or populate that this particular part has been changed or added, and now it is added. Now it is up to you that you want to add or not. So yeah. Yeah, please.
So my question is about, like, I know you mentioned the very common issue which we always like do the root cause analysis, like about the unable to. What about the false failure, right? So this is the one scenario which you shared. How how the AI can help us with the false failure, where like our script is good, but still we are getting the errors.
Okay, so our script is good, but still we are getting the error. Might be that it is not the locator error. Yeah, so related to the self-healing will not going to help this up, because self-healing is all about locator, changing the, if there is some modification has been done on the locator part. So it only handles the locator part. But later on, like if something else has been changed, so that might be the different feature which, can be provided by AI testing tool or not. So as I told in the previous slides, that we are having a lot of AI testing tool in the market, and different testing tools provide the different mechanism and the things it provides. So now I just choose one of them, and they are providing the self-healing. It might be that in another tool is providing this mechanism also, which you are saying. So it is up to user that how you are doing the R&D and picking up the testing tool. Yeah, please.
Okay, is it possible for this tool to take action during the test execution time? I mean, you hit this kind of error and such element, and Selenium will fix this during the execution, or after that the case failed, you have to rerun in order to get a success?
Okay, so the question is asked is if there is some kind of change that happen on the application, so AI will going to change it at runtime only, or after the execution it will change something, right? This is the question?
Yeah.
Okay.
Is there any way for this, before the test is marked as failed, to check, okay, we will face this problem, we will try to do the changes?
Okay, I got your question. So the answer is, it will ask that this is changed. Do you want to heal this? So if you do the I want to heal, it will heal, else it will not.
Okay, is that could be that automatic? I mean, my answer will be always yes. So, or I have to decide as a user.
I think you have to decide the solution. It could be like it possible that if you want to always ask the AI to heal, right? Yeah, but I think this is a manual task that you have to do. Okay, heal. Okay, do not heal this time. So this is how that you have to handle.
I think like you want to understand, like, can we automate this? Like,
yeah.
Give that
Yeah, because if I have a case that will always fail, why not to try healing?
Yeah, so it might be in the configuration of, you know, the AI tool. AI tool, it could be the separate configuration you can do. That skip this part, focus on this or something like that. So it is all about the configuration of AI-based testing tool. Yeah, somebody else was, yeah, please. Okay, so AI-based testing algorithm, what exactly the testing algorithm has been used behind it, right? So I think I need to do some research because I didn't know what exactly the algorithm has been used. As a tester, we just wanted to show that it provides you the heel locators or something that has been populated that is, you know, much deep into algorithm, deep learning, and so on. So that might be, we need to look up. Somebody else was there, okay.
So my question is going to be a little bit general. I don't know if you covered it in the presentation, but I'm just interested to know, is there any particular sector that is predictably going to be affected more by the implementation of AI? Just on the general perspective, not IT-wise or anything.
Mobile, I am unable to understand. Can you please just repeat mobile implementation of AI? Yeah, so actually it tells you all the data, but it cannot tells you that, it tells you or make a prediction about specific to your application because it got integrated with your application. So it fetch the data about that system and provide you the prediction, the future prediction related to that system only, like that application only. It cannot tell you that, okay, this might be a problem in the mobile or something like that, on which, you know, application you integrate, it only tells you about that. Yeah. Anybody else is having any questions? Mm-hmm. Okay. Intermittent issue, like not related to. So it comes under the flaky test case. Yeah, exactly. First, false failure and the flaky test case. So if you're using any reporting tool, it can easily tell you that, you know, this is a flaky test case and it doesn't count in that particular part. Yeah. Anybody else? Any questions? Yeah, please. I can't hear you.
Is it possible to automatically generate tests for specific functionality using AI?
Oh, to automate? I think it cannot automate from scratch. Surely it will not. But it can help you in eliminating the things that we do after we have automation script ready. So for the first time, you have to do, but after that, we have tons of things to do, we as a tester do, like maintaining a script, doing some changes to the script, you know, these many things. So, so these part of thing is been handled by the AI, not that from the scratch. Most welcome. Anybody else is having any questions? I think we are good. Thank you so much, everyone.
Hello? Can you hear me? My name is Dmitry Belevsky. I work in Red Hat since 2020. I maintain OpenSSL and OpenSSH there. I am also have honor to be a member of OpenSSL technical committee. My beloved pet project is also OpenSSL related. But today I will not speak about OpenSSL directly. I'm going to speak about introducing post-quantum cryptography in Fedora. So first, yes, I understand that all of those who came here understand what's cryptography for, but let me remind that for strawman understanding of cryptography it's ciphers, but experienced people remember that there is much more than ciphers. There are various integrity checks, there are digital signature, and anyway, when you want to just cipher something, you should provide a key to both parties, and it's also a task of cryptography. So we are waiting the moment when quantum computers appear and will break at least several parts of the cryptography applications. I'm speaking about digital signature and key exchange, but of course some other areas also will be affected. We don't know when and where the quantum computers will appear. When I first heard about it, it was in nearest 5 years, and it's still in nearest 5 years for, well, I say 20 years. Everyone can bet what happens before quantum computers or, say, nuclear fusion. But it doesn't matter that we should not be ready to the moment when they really appear. And so one of the organization management providing cryptography standards, American National Institute of Standards, initiated the contest of post-quantum cryptography in 2016. Here is some statistics. There were about 70 applications in the first round, and there were several rounds, and after the third one, in 2022, we got 4 algorithms selected for standardization, and we also get several algorithms to be studied for backup standards. One of them is broken since that moment. So here are the 4 algorithms that were chosen for the standardization. One of them is chosen for key exchange, and 3 are chosen for digital signatures. Almost all of them, except Sphinx Plus, are so-called lattice-based algorithms. Those who attended the first post-quantum presentation today here in this room several hours ago understand what's it. I don't pretend I understand anything in math. So just believe that they belong to various mathematical problems, and so breaking one of them will not break the other. Now let's talk about the standardization process at all. When we say that NIST has chosen an algorithm for standardization, well, it doesn't really matter, not nothing, but matters less than we can expect, because before turning the chosen for standardization algorithm into standard, there will be some parameters tuning, there will be something else, and it's not enough to standardize the algorithm itself. We also have to standardize how these algorithms, the keys, the parameters are stored in certificates, how they are used in various protocols. It's the area of responsibility of IETF. international task force. And we also should mention that post-quantum algorithms are also in the sphere of interest of OASIS group, which develops PKCS 11 standard, and as the algorithms will be used in PKCS 11 standard compliant decisions. So the NIST standardization is expected to happen in 2024. What it means for us? For us, it means that the next day NIST announced that they have standardized. We will get a bunch of clients' requests to implement post-quantum cryptography immediately. Yes, tomorrow. Yes. We should have already done this. Why we were sleeping all this time? We hope for the best. We hope that the other standards in the IETF and OASIS areas of responsibility will also be ready, and we also will be ready to provide something. But for now, we have a strict recommendation of NIST that nobody should provide commercial solutions on the versions that are not on the versions of post-quantum crypto that are not standardized. So we can't do much. What can we do now? Well, now we can use Fedora as a sort of playground, following our principle upstream first. Then at some moment, Fedora will turn into next version of Red Hat. And we should choose the library. And we should provide some experiments, see what are the narrow places of integrations of this library with the crypto libraries we maintain, and see how they work together, how different libraries are interoperable. I will talk about two libraries, OpenSSL, which is a base for all the server software, and for NSS, that is a base for such popular client software as Firefox, Internet Browser, and some other. So, NSS implements cryptography via PKCS 11 interface. That's why I mentioned the OASIS group and PKCS 11 standardization. And OpenSSL, a recent version we are going to play with, has implemented so-called provider API. It's a pluggable API that allows that in theory allows implementing any new crypto, and it will just work. Well, it's not true. It will not just work. At least it will not just work with the current OpenSSL releases, because some features will appear only in the next release, 3.2. But with the current release, you already, if you have some post-quantum implementing, some provider implementing post-quantum algorithm, you already can make some experiments. So we have to choose the library, and our choice is quite reasonable. It's LibOKS project. It's a sort of post-quantum ecosystem. Well, it's the library which is the standard de facto. As far as I know, there were several IETF hackathons, and all the projects that use something C-based use libOKS. This project, the authors of this project also have implemented OpenSSL provider, libOKS provider, and working in close contact with OpenSSL core team. Hi guys. They did their best, and current master supports, as far as I know, everything that can be done now until we have finalized specifications. Well, it also inherits, it also shares code base with another library, much smaller, PQClean, that will be the source of post-quantum algorithms implementations in NSS. So, it's the most significant slide in the presentation. Why you can't just say yum install libqs, libqs provider, and run experiments. Not because I'm lazy. Unfortunately, there are some license problems with libqs. Most of the code is licensed under the MIT license, which is not the problem. There are also parts of code that are licensed under other licenses which are fine for us, such as Apache 2, Unilicense, and so on and so forth. But there are some parts of code, unfortunately, the implementation of the algorithms that we are the most interested in under Creative Commons license, which is not suitable for including into Fedora as is. We will need an exception for it. We are working on it, and I hope that sometime later we will be able to include libqs into Fedora. So again, briefly reminder about upstream PQ readiness. NSS has some implementation based on PQClean, but again, we will meet the same license obstacles because it's exactly the same code license with a CCO license. OpenSSL regularly runs tests against the libqs provider, and they recently updated the version to the last current version of the libqs. But again, let me repeat, the changes are in master only. And last but not least, it's a discussion topic. We don't have a final solution among ourselves because libqs itself has several implementations of crypto algorithms. It can use OpenSSL-based implementation of low-level algorithms such as SHA-2 and SHA-3 and AS, or we can use OpenSSL implementation. It doesn't affect NSS. It's not a problem for OpenSSL, but we in crypto team maintain two more cryptographic library, GNU-TLS and libgcrypt. As post-quantum crypto is needed to be implemented in most libraries, at least at some moment, if we use OpenSSL-based build, it means that we provide some dependency between different crypto libraries, which has, there are good reasons not to do it, but it's a question of near future, not of just a moment. The nearest problem we need to deal with is the license problem. As soon as it's dealt, libqs will appear in Fedora Rawhide. Thank you very much. Feel free to ask questions. Alex. PHP, how ready is PHP? BGP? Oh, BGP ecosystem is not ready. Huh? PGP. There are some efforts in IETF, but I'd say they're limited. It's not the primary target of IETF standardization now. Yeah. Sorry?
It's storage, like the encrypt or whatever is used currently for encrypting your hard drive.
What about the cryptography used for encrypting the hard drive, right?
Yeah.
Yeah, so it's usually uses symmetric crypto, right?
Not for the key though.
Well, if wrap is implemented, it's not a problem to add post-quantum K wrap, if it's doable. I think it's doable.
So do you know whether is it ready or not?
I think it's not ready for now.
The network-based would be problematic.
Probably yes.
There's different protocols that are used, and stuff like if you're wrapping the key with RSA with a key recovery system, that's going to be a problem. That's going to have to change. Most of them, it's just if you're just using the log password, then that's your key generation, and that's quantum safe already. If you're using Clevis, then we have a lot of work to do still, because that's a whole new protocol which we need to figure out how it works with post-quantum algorithms.
Thanks, Bob. Thank you very much. Any more questions? Okay, thank you very much.